Hello, and welcome to Analog Devices Precision Training video, which focuses on switch and multiplexers technology. This video is the fourth in the series, entitled VT1004 Switch Charge Injection. The learning objectives for this video are as follows: to review some basic concepts about capacitor circuits, to explain the charge injection model, to explain the causes and effects of charge injection in circuit applications. Capacitance combinations are usually connected by either series, parallel, or a combination of the two. In series-connected capacitors, as shown in the figure, the total capacitance is calculated using the equation below. In parallel-connected capacitors, as shown in the figure, the total capacitance is calculated using the equation below. Capacitor charge is the amount of charge that moves into the plates of the capacitor and depends on the capacitance and applied voltage as shown in this equation, where Q is the charge in coulombs, C is the capacitance in farads, and V is the voltage in volts. To further explain this concept, let's calculate the amount of charge and the final voltage seen at the output of this example. If the initial voltage is 5 volts, C1 equals 10 picofarads, and C2 equals 1 picofarad, let's find the value of the charge, Q, through C1 and S1 is open. By using the equation, Q is equal to C1 times VI, which equates to 10 picofarads times 5 volts, equals 50 picocoulombs. When S1 is closed, the final voltage is calculated using the equation. Vf is equal to Q divided by Ct, equals 50 picocoulombs, the value that we calculated earlier, divided by the total capacitance of C1 and C2. The final voltage when the S1 is closed is equal to 4.54 volts. This is a short reminder that helps you understand the charge injection, as this involves the redistribution of the charge. Charge injection is a level change caused by stray capacitance associated with the NMOS and PMOS transistors that make up the analog switch. CMOS switches and multiplexers are designed using a PMOS and NMOS device in parallel. For both devices to have the same on resistance, the PMOS devices can be up to 3 times the size of the NMOS device. Therefore, the gate-to-drain capacitance associated with the PMOS device is about 3 times that of the NMOS device for a typical switch. The representation below shows the charge is injected into the drain output through the parasitic capacitor CQ, while the digital input is toggling. This cross-section of an NMOS transistor can be used to illustrate how charge injection occurs. Each step shows the charge injection processes. First step. A voltage is presented on the gate of the transistor, which attracts charges to the gate, forming a channel between the source and the drain. Second step. The source voltage, which is at negative 10 volts, in this example, is now connected to the drain and the capacitive load on the output, CL. Third step. When the voltage is removed from the gate, the charge that formed the channel disperses, with approximately 50% going to the source and the remainder going to the drain. Fourth step. This charge will cause a change in voltage, known as delta V. The change in voltage can be used to measure the level of charge, with the equation Q equals V times C. This method is how the charge injection is measured in switches. This shows the charge injection test circuit of analog switches and multiplexers. It shows the change introduced at the output of the switch when it is turned on and off. This can occur when switching any of the control pins to enable and disable the multiplexer. In the given figure, the V-in is toggling from 0 to VDD. This large step voltage injects charge to the output of the switch through the parasitic gate drain capacitance, CQ. The amount of charge is dependent on the value of the CQ. The change in output depends on the amount of the charge injected and load capacitance, which is composed of CD and CL. Since CD is much less than CL, the equation can be simplified using this formula. Based on this, you can see that the large load capacitance will minimize the effect of the charge injection at the output of the switches and multiplexers. Effects of charge injection can also be seen in bias control applications due to the retained charge in the switch capacitances when the channels are switching. This retained charge can cause transients in the switch output as shown in the figure below. Assume that S2 is initially closed and S1 is open. CS1 and CS2 are both charged to -5 volts. As S2 opens, the -5 volts remains on CS1 and CS2 as S1 closes. The output of the amplifier A sees a -5 volt transient. The output will not stabilize until amplifier A's output fully discharges CS1 and CS2 and settles to 0 volts. The scope shot in this photo depicts this transient phenomenon as shown in the boxed area. Therefore, the amplifier's transient load settling characteristics will be an important consideration when using the right input buffer. In summary, the charge injection is the amount of charge coupled during switching for the digital output to the switch output. It causes a change in output voltage, called delta V. It also introduces dynamic transients at the switch output in the bias control application. Large load capacitance reduces the effect of charge injection. In the next part of the series, AC and timing parameters will be discussed. For more information, kindly visit analog.com/switches multiplexers.